Hey everybody, I want to talk to you a little bit about some logarithms, specifically with bases that we haven't talked about yet. So logarithms and exponentials with base e and base 10. We've done a little bit with base 10, but I really want to talk about base e. That's the most interesting and most important of the logarithms. So anyway, let's get started. And I want to start this off in kind of a non-standard way. I usually do a pretty, straightforward presentation of what we're working on. But today I want to present things a little bit differently. I want to talk about compound interest and where we're going with that. So compound interest works like this. Every so often, you get interest from the bank. If they tell you that the rate is 6% per year, they don't just calculate it one time. It's not like you only get interest on January 1st and they just take 6% of whatever you have in your bank account then and tack it on. It's not how that works. What they actually do is they calculate interest as you go along. Right? I think most banks calculate it every day. And so what that means is they have to break down the time period that they are giving you or how frequently they're giving you interest. But they also have to break down the rate. So let's just do it once per month, right? This is not how it's actually done, but let's do it once per month just as an example, right? So if you recall, the amount of money in your bank account at time t is equal to principal A0 times 1 plus your interest rate to the t. Now this assumes that the interest rate is just applied one time, and that t here is in years, right? So the idea is that if you have 6% interest, and then t is some whole number of years, this is how you would calculate the interest. But that's not actually how it's done. So let's say they're doing it once per month, right? So t is still going to be in years, but we're going to do this once per month. So I'm going to call that number the number of times we calculate interest per year. I'm going to call that n. Right? So I'm going to say n equals 1 for this. 1. And then what I'm going to do is for n equals 12, n equals 12, we're going to recalculate the formula. So what's going to happen is every month, they're going to give you a 12th of the percent that you earn for the year, right? So if you earn 6% for the year, and they're breaking that into 12 pieces, they give you 0.5% every month. This turns out to be not exactly the same, but pretty close to 6% per year. It's actually a little bit more. So we get A0 times 1 plus. Now, if we're doing this 12 times, we're going to break down the interest rate into 12 pieces. But we're going to give it to you 12 times as often. So we get something that looks like that, where the way you calculate the interest is 1 plus r over 12. So you get a 12th of the rate, but you get it 12 times as often. This actually works out very slightly in the favor of the person who's earning interest. It's a little bit more. It's not a lot more, but it's a little bit more. And more generally, what you get is, if we're going to do this n times per year, you're going to break up the interest rate into n pieces, and you're going to give that to them n times in a year, so nt, number of times. And this is your compound interest formula. This is your general compound interest formula for any number of times compounded per year. Compound interest formula. Now, I believe I don't actually know. I didn't do any research before doing this video, but I believe banks typically do this once a day. All right, so they calculate the interest one time per day, I think, when they close. And so that what they do is t is 365 for them. Or n is 365. So they do it one time per day, and then yeah, that's about as far as I know. So there you go. That's how you would do the compound interest. Let's do you want to see an example? Sure. Let's do an example. Right. So let's say Veronica deposits $1,000 on January 1st, January 1. How much does she have next January 1 if her nominal interest rate, which is what I'll show you what that is in a second. Nominal interest rate is 5%. Percent compounded A annually. B monthly. Or C daily. All right. So what we want to do is we're gonna use this formula, the compound interest formula, this guy right here, 1 plus R over N to the MT, to figure out how much Veronica is making, or how much interest she earns after 1 year. After 1 year, assuming the interest is compounded annually, monthly, and daily, each of them at 5%. So, come on, computer. So let's do annually. The annually means one time. Annually, my n's and u's look exactly the same. Sorry. So we have n equals 1. So we're going to say that the amount after 1 year, 1 is going to be A0. So the amount she deposited originally, $1,000 times 1 plus R over 1. Oh, sorry, R is 5%. I know 0.05 over 1 is 0.05 to the t, right? To that 1 times t is 1 year. So what you get is 1,000 times 1 plus, or I guess I'm going to write this as t for a second, 1 plus 0.05 to the t, exactly like we've done before, right? That's what we did when we were calculating compound interest and population growth and a bunch of other stuff. And I just realized I don't have my calculator open, so I'm going to have to pause the video for a second and go open that because it takes like 3 minutes to open. Actually, instead of using the VMware calculator, the TI-83, I think I'm just going to do it on Desmo. It's still a little quicker. So yeah, let me share that up. I'll show you what we're doing here. This guy? Yes, this one. This is the one I want. So here she is after 1 year. 1,000 times 1 plus 0.05 to the 1. All right, let's see what happens if we are compounding that monthly. Was monthly the second one I did? Monthly and then daily? Yeah, monthly. So n here, let's switch back to the whiteboard. N here is going to be 12. Monthly. It's not the neatest, but you get the idea. So n equals 12. So we're going to have A of t is going to be 1,000 times 1 plus R over N, so 0.05 over 12 to the NT. Well, T is 1, but N is 12, so we got 12 times T. So this is going to be 1,000 times 1 plus 0.05 over 12 to the 12th power. Right, so what we're getting is a 12th of the 5%, 12 times a year. So about 5% at the end, but you're going to see that it's actually not quite the same, although it is close. Right, so we're going to have 1,000 times 1 plus 0.05 over 12 to the 12th power. So she actually makes $1.16 more, right? It's 1,050 even if you just compound it once. If you split the 5% up 12 times and up into 12 pieces and do it 12 times, you get a little bit more, 1,051.16. What if we did it into 365 pieces? 1 plus 0.05 over 365. And we're going to do that 365 times. And it's a very little bit more. It's an extra dime, right? 1,051.26 instead of 16. And so it looks like this, like the increase, it increased a little bit, right? When we went from daily to monthly, n goes from 1 to 12, it increases by $1.16. And you might think, well, if we go from 12 to 365, it's probably going to increase more. No, only 10 more cents. Let's say we broke it up hourly, right? So 365 times 24, right? So now we're not just compounding every day, but every hour of every day. 1,000 times 1 plus 0.05 divided by, this is going to be 365 times 24. I have no idea what that is, times 24. We're going to compound that 365 times 24 times. Times 24. Oh, nope. Up here. Times. No, it does not like that. Okay. Gotta put it in parentheses. Times 24. Right, so we're compounding. Every hour we gain 0.3 pennies. Right? So it really looks like making n a little bit bigger changes or increasing n by a little bit from a small value to a somewhat larger value increases it a fair amount, but making it much bigger doesn't really seem to do much, right? I could make this 1 billion here and that 1 billion there, and it wouldn't really change much. It would be pretty much the same thing, right? We would be gaining fractions of a penny at most, whereas when it went from 1 to 12, we gained like $1.15, which is like a little bit more. And so it really seems like as n gets very big, this formula stops changing all that much, right? In an effective sense, right? The numbers get huge, but it doesn't really change much effectively. And that's the case. So the thing that's happening is the following. We've got something that looks like this. 1 plus 1 over x to the x. And this is sort of being all raised to the t power, right? So yeah, that's where I'm going with that. Where x here is kind of playing the role of n, right? This is very similar to like if my interest rate was 1%, n goes here, and then we multiply this by 1 because we're going for 1 year. And so this is kind of what we get. So what we get is something that looks like that if I graph it. And you can see it starts going up relatively fast at first and then slows down dramatically, right? It's not going up hardly at all after that. Looks like it's leveling out at about 2.6, right? There's 5 things, there's 5 blocks in here. It's a little bit above 2.6, right? And if I go to the right, it's getting a little bit bigger, so maybe 2.7. But it's really pretty flat at this point, right? And so changing the x from like 32 to 33 really doesn't do much as far as the vertical change. As you may have guessed, the number that this is headed to is e. It is a constant that you may have heard of, may not, I guess, which is this number right here, 2.71828, right there. And you can see that that is indeed what this is headed for. And so this is called the, well, this isn't a logarithm of any kind yet because I'm not using it in a log, but we will. This is the base of the natural logarithm. And so the natural logarithm is the one that occurs most often in nature, basically. That's essentially why it's called the natural logarithm. It's a thing that comes up a lot in applications. And you can see that the green line is indeed getting very close to the red one. I'm zoomed in quite far at this point. And so this is why we care about E, the constant E, which I guess I should introduce it a little bit. E is a constant. It's sort of like pi in the sense that it is an irrational number. It just goes on forever without terminating or repeating. Yeah, it's about 2.7. That's really the thing to know about it. When you get to calculus, if you go that far, you will end up using E quite a lot. It is one of the 2 or 3 most important numbers in all of math, right up there with pi and your basic small integers like 1 and 2, things that you see a lot. It's super, super important. And this is a thing that often gets lost in the mechanics of what you're doing with it, but you're going to use E a lot. Like the farther you go, the more you'll use it. And so this might be a nice introduction, but this is what it is. E is what happens to this expression, 1 plus 1 over x to the x, as x gets really big. Like that's actually how we arrive at E. I'm not going to derive that for you because it requires a little bit of calculus, or at least some calculus concepts. And I think that's a bit much for an intermediate algebra video. So yeah, just suffice it to say that it is it's what happens to this expression when x gets really big. And the reason we care about that is essentially this thing that I just showed you, is that basically when you subdivide time into smaller and smaller pieces, exponential growth tends to look like exponential growth base E, because of this. But once I've said that, that sounds super vague, and it is. Sorry, but that is the essential reason. Is there's a lot of things that look like this in nature. This is what exponential growth kind of looks like, and so yeah, I want to show you around these log bases real quick. Now, there's actually not much to say here. I'll just write out the basic, or what we're talking about today. So there's 2 logs that get used more than others. There's a log base E of x, and we don't usually write it as log base E. We write it as ln. That's not an I, that's an L. That's ln for natural logarithm, and I believe this comes from the French for logarithm naturel. That's why it's ln of x. So if we're using the base E, so if you see ln of x, it means that the base is E. If you just see this, it means that the base is 10, at least in this class. There are some mathematicians that like to use this for log base E. I don't know why. Just get with the program and let everybody be the same. I'm not going to do that. I'm going to do this is log base E. Oops, I did this one backwards here. This one's log base 10. We're just gonna select this and delete it. Then I'm going to realize that looks really funny. We're going to select that and delete it and rewrite it. Log of x. Right. So that's the basic idea. There actually isn't a whole lot more to say, to be honest. Yeah, we'll do a couple of problems like this, but this is just a shorthand notation. If you don't see a log base, if it says log, that means the base is 10. If you don't see a log base and it's ln, that means that the base is E. There you go. Sorry. So ln of x, this is the inverse of e to the x. E to the x. This is the inverse of 10 to the x. 10 to the x. Right? Because that's what logs are, right? They're just the inverses of exponentials. So when you are solving exponential equations, which we'll do a little bit of in a future topic, and you've got e to the x that you're solving, or that in the equation you're solving for, you probably want to use the natural logarithm to well, you'll see when we get there. You'll probably want to use a natural logarithm. If you have a 10 to the x, you probably want to use base 10 logarithm. Yeah, that's honestly about all there is to it. We'll do a couple problems, then call it good. I guess what I want to say is this: if I have my general compound interest formula, a of t equals a0 times 1 plus r over n to the nt, if you let n go to infinity. So I'm going to let n get really big. What ends up happening, because of that thing that I said before about e, is this. If you let n go to infinity, you get a of t is a0 e to the rt. Because this 1 plus r over n, or 1 plus r over n to the n, turns into e, essentially. The 1 plus 1 over n at the end turns into the e, and this r and the t end up in the exponent. I'll just leave it at that. I can derive that for you if you want. It's actually kind of interesting to do, but not super relevant to what you're doing. You might also see this written as pe to the rt. Pe to the rt. Hurt formula. I'm not as wild about using p here instead of a0, because the idea of p specifically stands for principal, right? So this formula makes the most sense in terms of compound interest. But it turns out that basically every exponential growth formula is pe to the rt. And thinking of p as principal kind of limits it to money. So I prefer to call it a0 e to the rt. But if you want to call it PE to the RT, that's fine. That's what most people do, to be honest. So yeah, what ends up happening as you let time get subdivided into smaller and smaller chunks, so you're increasing a smaller percentage every time, but you're doing it more times, this formula turns into this formula. Yeah, and that's why this is considered the base of the natural logarithm. I realize this is an exponential, but of course you'd use a natural logarithm to solve this thing. But that's why E is so important, because there's a lot of things that grow exponentially. And if they grow exponentially in a smooth fashion, then this is the formula that you would use to figure out how big they are. So let me pause the video for a second or two. I'm going to get a couple of examples to do, and then we'll do them. I think I'm going to build on my previous example. I think that's going to be the nicest example I can do. So we got Veronica here. She deposited $1,000. And so I'm going to tack on a part D to this and say continuously. So what if her compounding was continuous, where n equals infinity? So in that case, Veronica would not be doing, can I rearrange the pages here? Not really. Veronica would not be using this formula, A of t equals a0 times 1 plus r over n to the nt, because we can't really put infinity in for n. Instead, we do a little calculus, and it turns out that this turns into, so we let n go to infinity, then that means that a of t for Veronica is going to be I'm not going to use p, a0 e to the rt is going to be what she gets. So r was 5%, and a0 was $1,000, so we have 1,000 times e to the 0.05 times 1, right? So this is going to be 1,000 e to the 0.05. That's the amount that we're expecting her to have if her interest is compounded continuously, which nobody actually does continuous compounding, because that would mean that depending on the time of day that you checked on your money, you might have a fraction of a penny difference, which gets a little weird. It's just easier for banks to do it once a day, I think. So I'm going to go over to Desmos here. So we're going to do 1000 e to the 0.05. And lo and behold, that's the limiting value. Notice that that is as big as this would ever get. No matter how big I made n, it's only going to be limited by 1051, 27.1, right? So we basically had that already. Doing it daily, 1051, 26.7 instead of 27.1. You might notice that this is not exactly the same amount of money, even though I'm technically using the same percentage rate. I'm using what's called the nominal percentage rate here of 5%, which means you say that it's 5%, and it's 5% if you calculated it this way. But that's not actually what the rate is. The rate is actually very slightly higher than the nominal rate, depending on how often it's compounded. You can see instead of 5%, it's actually like 5.1% when they are compounding it daily. And that's really all there is to it as far as E goes. The only other things I wanted to mention were that E and 10 end up being used a little bit more often than other bases. E, because it shows up so often in nature and natural applications. 10, interestingly, because at least as far as I know, as a mathematician, I don't know why other people use log base 10, but log base 10 of a number is how many digits are in that number if you round it off. So if you do like log base 10 of some large number, the thing that you're going to get is how many digits it has. And I guess I will, so if I did like this, log base 10 of 159531784 I can actually estimate that pretty quickly. 369. It looks like that's about 10. Yeah, let's do that in Desmos and see what it gives us. I can't copy paste this, so I'm gonna have to go about 159. Oh, I should have done something smaller. 15. I'll just do something in Desmos. So if I wanted to find log base 10, base 10 of 1595. What did I do? Why did I pick such a big number? 317846. 746 maybe. A little bit bigger than 9, right? Even though it has what, 10 digits. So I was a little bit off, but that's a shorthand quickie approximation for how big something is, or for how many digits it has, is what its log base 10 is. The other time that you might use log base 10 is with scientific notation, right? Scientific notation has a bunch of 10 to the power of something, and so you might use log base 10 to talk about just the power, basically. And we'll get into that more with when we do a little bit of solving and using logs to cancel exponentials, which is where all this is going in the first place. Yeah, but I'm going to go ahead and leave it there. There's not much more to say other than, E is a number. E is about 2.71828182845 something, I believe is about what it is. And we end up using log base 10 a fair amount with scientific notation, or if you want to know how many digits a number is, 10 to the power of something, or 10 to the first is called an order of magnitude. So like 10 to the third is 3 orders of magnitude. And so this counts orders of magnitude. That's what log base 10 does. All right, I think I've started rambling a little bit too much. I'm gonna go ahead and stop the video there, and I will see you guys in the next one.